Okay, this is NeuroDoc's submission for the US Imagine Cup. So NeuroDoc is an automatic neurodegenerative disease detector. The team that worked on it is myself, Brendan Alvey from the University of Missouri, Suyash Gupta from Purdue University, Pranjal Daga, also from Purdue University, and Evan De Santaloa from Carnegie Mellon University. So a brief history about this project. I actually just met the other three of those 9 days ago at HAC Illinois and University of Illinois Urbana-Champaign. We built this thing in less than 36 hours. We actually took home the top software hack. We also took the Microsoft's best hack and Microsoft's best use of Azure. And so this was a competition over 3 days with more than 1,200 very talented electrical and computer engineering students, computer science, IT, everything. It was a great mix of people. And so to motivate our project, we knew that many diseases, specifically neurodegenerative diseases, produce tremors and stutters, and that maybe we could detect this using data that's already sort of out there. To go with that motivation is that early and accurate detection is going to be key to treating these diseases, hopefully preventing them, which will save money and hopefully lives. So how did we detect, or how did we try to detect these diseases? So we said that there's 3 data sets out there that we could probably use here. We said handwritten signatures, whether when you go to the gas station and you swipe your card and you sign your name, that data is going somewhere for verification, but it's not really being used, as far as I know, or as far as we know, for detecting diseases or anything like that. We also said that speech samples, specifically from your phone calls or just when you're talking to your phone and asking it what the weather's like, that data could be being used for something else. We could be using it to detect abnormalities in speech and specifically stutters. Also, accelerometer data is becoming more and more abundant. Most smartphones come with pretty high quality accelerometers, and wearable fitness is becoming more and more popular. And all of those devices have pretty high quality accelerometers. So first we looked at accelerometer data, and at the HAC Illinois competition, we were allowed to use these Myo bands, which are wearable fitness devices. They have pretty accurate accelerometers, 3 axes. They give you X, Y, and Z sort of acceleration as you hold them. So what we did was we said, okay, just to begin with, can we place the band sort of on somebody's hand and then tell them to hold their hand as still as they can for about 30 seconds. And so on the far left there, we have what a healthy person's data might look like. And so if you notice, there's not much variance in each of the axes. They're all pretty still. Now, the middle one was actually a pretty realistic sort of tremor that we had, that we tried to simulate. And so if you notice, there's much more variation in each of the dimensions. And likewise, on the far right, we did a sort of an exaggerated tremor, because at this point we didn't know if we could process the data correctly or if we could actually parse out useful information. So we wanted to sort of test it until it degrades. So we had to do a little bit of pre-processing in order to do our comparisons here. And so you probably can't read it, but on the far left here, each of these is on a different scale, for what makes sense based on the data. So what we did was we subtracted the mean to bring all of this data to be centered at 0, and then we just summed the square of them. That way it's sort of like adding the absolute values. And when we looked at these amplitudes, they were vastly different. So on the far left, the sort of healthy hand was at 10 to the minus 3. This middle one was at 0.5, and this far right one was at 0.9. And so that meant that we had a very big difference, and we could just use a threshold if we wanted to. So what we did was we just set a threshold of 0.01, and we said, let's find the percentage of the data which is above that, and use that as sort of a score. So it actually worked pretty well, and these results are pretty reproducible. For the normal accelerometer data, for the healthy accelerometer data, we got a score of 0.085. For the small tremors, we had 0.935, and for the large tremors, we had 0.981. So this was very promising results. Now the next data set we looked at was handwritten signatures. You may not be able to tell, but the bottom one is quite a bit more wavery than the top. It's actually, we tried to simulate what a signature might look like if you were suffering from tremors. And so we thought, while these are definitely a lot more similar than the previous data set, there should be something that we can pull out of here. So the first thing we did is we pre-processed this data because we want to be able to do comparisons on it. And all these images might come in looking different. All these signatures might look a little bit different. We have to somehow get them all looking a little bit the same so we can do comparisons. So the first thing we did was we converted it from a standard color RGB image to grayscale to binary. That's a pretty standard transformation, and it was actually pretty easy because signatures are usually written on highly contrasting backgrounds, so that process is usually not too complicated. But then we needed to rotate the image, so we used the principal component. So in principal component analysis, we look at the dimension of most variance and its orthogonal direction of next most variance. And so we use that principal component, and as long as the signatures are wider than they are tall, this should work. We used this principal component and we checked its rotation angle with respect to the horizontal and just applied an affine transform to rotate it. We also then mapped everything to a common grid. We kind of trimmed on both sides so that all the images kind of fit the whole common size. So once we had this sort of pre-processing step figured out, we constructed a dictionary of healthy signatures. And when we have a new signature and we want to know if it's healthy or not, we compare it to this dictionary. So if any one of the dictionary elements matches well to this new test image, then we say, good, it's healthy. But if it doesn't match well to any of them, then it's abnormal. We haven't seen it before. It's anomalous. And so as you may imagine, that the scores are closer than the accelerometer data. They're less separable, perhaps. But these are pretty reproducible, and we are actually able to notice the difference over and over again between the healthy ones and the not healthy ones. So the next problem was we went on to try to analyze speech data. And then speech data is inherently a much harder problem, but we were able to make a little bit of an impact on it. So if you look on the left here, we have what maybe a healthy person's speech might look like. And if you notice, all the waveforms are relatively smooth and non-repeating. But on the right here, we simulated what stuttered speech might look like. We actually just recorded stuttering speech. And if you look particularly in this first one, we see sort of a repeating pattern of a similar amplitude and similar sort of waveform. And so we thought maybe there's something we can extract here. How could we do this sort of features? So when we wanted to do the comparison originally, we thought maybe we could do this in the time domain. But since these are all sine waves, if two sine waves are just a little bit out of sync and we try to do our comparison between them, our results wouldn't make much sense. So we thought maybe we could look at the frequency domain in order to do this comparison. So what we did was we said, okay, a stutter is about 0.15 seconds or so. It's just a rough estimate, but it worked for our purposes. So we divided the whole speech signal up into 0.15 second windows, and then we computed the fast Fourier transform over all of those. And what that does is it gives us sort of a frequency analysis of each of these window segments. From there, we just looked at these segments and we compared them to each of the other segments, and we looked for which one did it match closest to. So for instance, if we wanted to figure out if this first sample, this first window, was a stutter or not, we compared it to each of the other windows that came afterwards, and we noticed it matched really good to this one that was a 3 down from it. And so we just score ourselves with this very simple equation, 1 over 1 plus d, where d is the distance to the best matched one. So in this case, we'd say, okay, d, we best matched to 4, but it was number 1 that matched to it. So we take 4 minus 1, which is 3. We take the absolute value in case we matched to 1 before it. And we just do 1 over 1 plus 3, which gives us 0.25. Now, when we actually implemented the code, we scaled these by 2 so that we subtracted 1 from d so that if we were right next to it, we got sort of 0 and we get a 1 out of here. Now these scores are a little bit, I don't have slides on it, but the scores here would kind of vary throughout the entire speech. And so in order to determine sort of what exactly we called a stutter, or how many there were rather per, say per sample, we invented this sort of adaptive thresholding function, which uses the geometry of sorting this all in order to make it work. And so we have a quick little video of the code that we showed at Hack Illinois. We've since updated it with new CSS and everything, but it didn't make it into this video, unfortunately. And so I'll just play a little bit of the clip of what NeuroDoc, sort of a prototype from just a few days ago, looked like. And so we have this web app, and you choose an upload file. And first you upload the myo data, the accelerometer data. From then, you upload a speech sample, so just a WAV file or an MP3 file. I should note that the accelerometer data comes in as a CSV. It's sort of like an Excel table. And then finally, we upload a training set for the images, and then for the handwritten signature images, and then we upload a new one where we want to know, is it good or not? And so at the very end, NeuroDoc will give you scores for each of these, and it will give you a recommendation based on sort of data we've seen before. Are these scores, typical of a healthy person, or are they not? And so our idea is that we can expand this quite further. We can use all different types of data. We could probably incorporate heartbeat sensors. We could use galvanometers and all sorts of things. And the idea is that this data is already out there, and for the most part, it's just being used for advertising. But it could be used to save lives, and everyone could benefit from this thing. Everyone has a smartphone, and so there's tons of data points that could be being used to monitor patients outside of the hospitals, to work with clinicians and doctors to do diagnostics. And so that's just sort of our idea, and we really think that if it saves even one life, then it's a winner. Thank you.